Hello, my name is Tim, and I'll be your guide through HVAC. Today we're going to talk about single-phase motors as it relates to HVAC, or this could actually be applied to any single-phase application. For HVAC, you're going to find single-phase equipment in either 230 volt, 115, or some arrangement other than that. That will include compressors starting, or a blower motor, or a condenser fan motor. So how do these things start? Well, obviously you're going to have your stator coil, and your stator coil is going to be made up of two sets of windings, the primary and the auxiliary, which we often call the start winding. Additionally, you're going to have your rotor. Now, the stator will induce a current into the rotor. The problem is that when we do that you're going to have a magnetic field that is opposite with the same overall torque. That means it's going to lock in. You're going to have a problem. For example, in this motor right here, single phase 115 induction motor. I simply apply a current signal to the primary winding, as we can see here, that the primary and the auxiliary windings are perpendicular. The intent is that I will induce a current into the rotor with the primary windings. However, I use the auxiliary or start windings to give it higher torque on the rotor, which will actually start the rotor off. So for example, in this motor right here, if I simply apply 115 volts without my auxiliary winding, all it does is hum, unless I physically get it going. Now, that would be wonderful if I had someone to push this every time I went to start it. However, it becomes completely impractical. Tesla came up with an excellent idea, and that is the secondary winding, auxiliary winding, or start winding, whichever you want to call it, making them perpendicular to the primary. So our auxiliary is now perpendicular to our primary winding. We add a capacitor to give us that additional torque and give us a 90-degree phase shift. So if we look at here, we're actually going to have a 90-degree phase shift between the start and the run winding. This will give us that additional torque that is induced into the rotor to actually get it going. In our case, here's our capacitor, and if I simply turn on the power, without the capacitor, it won't run. I add the capacitor, it gives it that 90-degree phase shift, which actually allows the motor to continue to run and start. Now, with a simple set of primary windings, we can get a very strong magnetic field, as I'll demonstrate with this coil. So this coil, I'm going to put AC current single phase to it. It's going to create an electromagnetic field. Allows us to magnetize. Great if we want to keep that magnet and pull something in. If we're going to use this for, let's say, a coil for a solenoid valve, as we see here, here's the windings, and we'll have some metal in the inside with that plunger to pull it up. Here's the plunger. And the electromagnetic field will actually pull that plunger up and allow flow. Or if we have a contactor, or even a larger contactor. This allows us to simply create an electromagnetic field that's continually changing poles, north, south, and allow us to create an electromagnet. In the case of the motor, We've got our electromagnetic field, but the motor that by itself doesn't move until I actually create that 90-degree phase shift. When I do that, the motor is now able to continue to start. Capacitors come in various sizes and shapes. We have metal, which is usually a lower capacitor rating, or we have, which is normally considered to start, a ceramic style capacitor. These are rated for the work that you're going to do to start that motor. Now let's talk a little bit about the windings themselves. If you look at the diagram on top, we have both the run and the start. And when you're looking at compressors or on any system that has a set of start windings, you're going to have a common, start, and run. The highest resistance is between start and run. The lowest resistance is between common and run. The second highest is between common and start. This is for a reason. The lower resistance between common and run provides a stronger magnetic field. The resistance between common and start, which is slightly higher, makes sure that the current, after it's started, will go through the common to the run winding. When we go to start this motor up, we're going to have very low resistance, so its natural 10 is going to go to the lower resistance. That means that initially, the lower resistance in the run winding, you would think would start it. However, because it's got lower resistance, it's going to have much higher current, which means the overall impedance is going to be higher. So the current will actually go through the start winding first because of that 90-degree phase shift. Then once the start winding is out, the lower resistance, the current will come down, which will lower the impedance, and now you'll just be using the run winding. So this is our introduction into single-phase motors. Please continue to watch, and we will continue this into other areas of interest. Thank you very much. Have a wonderful day.